So it's a great pleasure for me to open this series of Simon's lectures this year. We have with us Professor Isadore Singer from MIT. Professor Singer has a long and distinguished history in both mathematics and physics. He received his PhD from the University of Chicago in 1950 under Irving Siegel. He was appointed the Norbert Wiener Professor at MIT in 1970. He, in 1983, was made the first John D. MacArthur Professor at MIT and is now an Institute Professor. And he's won a number of prizes, including the Bechet Prize of the AMS, the Wigner Prize, and the National Medal of Science. He's been a member of the National Academy of Sciences since 1983 and sits on the council of the Society. He's a member of the American Philosophical Society and the American Academy of Arts and Sciences and so forth. He served on the White House Science Council for a number of years, advising the president. And probably of most interest to us here, he's been one of the most profound and original contributors to differential geometry and analysis of preceding decades. He's really well known to both mathematicians and physicists for his contributions to the index theory of elliptic operators in many forms. Also to deep and original results of spectral theory, eta invariants, and asymptotic expansions, the heat operator. But one of the things that has made him
bringing together over the past several decades mathematicians and physicists, not people who naturally sit between, but people who are really often in two worlds working on their subject. He's done, I think, of all mathematicians who've worked in both of these worlds, none has approached his Singer in the level of energy and accomplishment that he's brought to this monumental effort of bringing mathematicians, bridging the two worlds, building highways between mathematics and physics. So for me, it's a great honor to introduce him. He'll talk today about the Index Theorem revisited.
Thanks, Blaine, for that very laudatory introduction. I'm very happy to be here again. Wish I could visit more often. And I'm particularly pleased to be the Jim Simons lecturer. Many of you do not know that it was over 20 years ago that Jim introduced me to gauge theories. He told me of the luncheon seminar he held with Frank Yang, and he told me of the dictionary between gauge theories in physics and fiber bundles and connections in mathematics. In early '76, I read the famous Wu-Yang paper, which gave the little dictionary between gauge theories, the elementary concepts in gauge theories, and the elementary concepts in fiber bundles. Later that year, I learned of the self-dual Yang-Mills examples of 't Hooft and Polyakov and company. And in fact, this month is 20 years that I gave a series of lectures in Oxford, November and December of 1976, in which I talked about the Wu-Yang dictionary and gave the 't Hooft Polyakov example. In fact, wrote down the first global geometric example of the self-dual Yang-Mills. I had a very receptive audience, I must say, at Oxford at that time. Atia, Graham Siegel, Hitchin, and Penrose attended my lectures, and we had a wonderful time. So I'm just emphasizing that Jim really pointed me in the right direction then, and I think it was exciting to see these connections between mathematics, geometry in that case, and high-energy theory. I went on to Berkeley and started lecturing on the quantization of gauge theories at the beginning of '77 in order to learn the subject. And I think the excitement has increased in the 20-year period. At any given time, I think it's about to come to an end, but no, It just grows. Well, if you don't mind, I'd like to take another 5 minutes off to tell you what I want to do in these lectures, and also to introduce my point of view in today's lecture. I want to talk about string theory. Before I do so, a disclaimer. There's a lot of controversy in the physics community as to whether string theory is going to have an impact on physics. I'm not qualified to even have an opinion on that subject, and I don't have an opinion. But certainly string theory has had an enormous impact on mathematics. And that impact, I think, will continue and grow stronger. And the point of my lectures is to particularly motivate young people, when they're still young, to learn both the requisite mathematics and from experts in the field, and the requisite physics from the experts in the physics field, so that they not only can speak both languages, but they can begin to think the way these two different groups think. I don't really think I can accomplish that in a few lectures, but at least I can show you a little bit about what's going on. So let me say a word or two about string theory. For our purposes, string theory is taking theoretical physics and putting a new category of doing theoretical physics, not for ordinary manifolds, but replacing points by loops. So where you see a manifold, you replace it by loops on a manifold. So that's our first category. We're going to replace a manifold by loops on a manifold, and then we do theoretical physics all over again. So if you think about Lagrangians on the tangent bundle and Hamiltonians on the cotangent bundle, then you want to do that for the tangent bundle of loops on a manifold. What's the tangent bundle of loops on a manifold? They're just vector fields along the loop, etc. If you're going to quantize on the symplectic manifold of the cotangent bundle, then you're going to have a Hilbert space instead of L2 of the manifold, or some geometric quantization. You need to have something more complicated where you're going to quantize L2 of, say, loops on a manifold with the right measure. If you're going to talk about a Laplacian, you need, or a Schrödinger operator, Laplacian plus a potential function, you've got to do that on loops of a manifold. If you're going to talk about the Dirac operator, you've got to replace it by the corresponding what's called the Dirac-Ramoned operator on loops of a manifold. And the idea is you just carry out this whole program of doing physics all over again. The reason physicists are excited about that program is that when you look at the physical Hilbert space, it turns out that in that Hilbert space is a spin-2 massless particle, and therefore you're able to quantize gravity by this procedure of going to loops on a manifold. That's the original excitement of dealing with string theory. Of course, extended objects in physics, place points by extended objects, by and large, you're going to run into trouble very quickly. Lorentz group, contraction, etc. One had tried that with the electron. It doesn't work. You immediately run into difficulties in string theory. And it turns out in the associated Hilbert space, there is a particle of negative mass. You'd think physicists would give up, but no. What they do is introduce another category called supersymmetry. It takes an ordinary field and associates with it a matter field, a supersymmetric partner, and by introducing supersymmetry and using it properly in the string theory, what's called superstring theory, they eliminate this particle that doesn't make any sense physically. So the two new categories in which you want to do theoretical physics is supersymmetry, string theory. And now you proceed along and you think that you're going to run into problems all over the place. Well, it turns out that every time you run into a problem, all you do, what physicists say, is you restrict the possibilities. So mathematicians want to do physics in any dimension. It turns out that the only place that you can do superstring theory is in 10 dimensions. So what this does is tell you you'd better work in 10 dimensions. And then the problem is, how do you get down to 4 dimensions? What you do is split your 10 manifold into 2 pieces, ordinary space-time of 4 dimensions, and then a fiber, which will be a compact space, and then you want to see what the effect of this compact fiber will be on your physics. There are a lot of other problems you run into. Anomalies show up, saying various things you don't want to appear. You use index theory to tell you of how to eliminate those anomalies. It restricts the gauge group that you're going to be dealing with, etc. So you have this whole procedure in which you would think, I would have thought, looking at the subject, that you'd end up with the empty set before you're finished. And what physicists hope and believe is that you're going to end up with a unique theory. However, up until 2 years ago, they had 5 different kinds of string theories. And that bothered physicists because they were looking for a unique one. They wondered which one of these 5 was the right one. And the excitement over the past couple of years is the introduction of various dualities called S, T, U dualities, in which it turns out that different kinds of string theories are really the same. I don't mean to say by that all string theories are isomorphic. It's much more complicated than that. But in some sense, you could say that there's really only one kind of string theory with various manifestations. I don't have the vocabulary, or I should say you don't have the vocabulary for me to explain what that means. But the excitement in the last couple of years has been that all these string theories are really the same, so that there's only one kind of string theory, and in fact there should be some super theory which explains how you see these different 5 theories in different ways. Another excitement of the development in the past couple of years is that one of the string theories, one that I'll come to perhaps by the end of today's lecture, you don't see the gauge group at all. You don't see gauge theory, you don't see a Lie group. You just see maps of strings in the sum manifold. Where's the gauge group coming from? And just like you saw a graviton, a spin-2 massless particle in ordinary string theory, what happens in this theory is that you see the Lie algebra of the gauge group in the associated Hilbert space, and so you recapture gauge theory in a way almost free of charge. And it happens in a very geometric way. You're sitting in one of these 6-dimensional spaces. You're moving around in it. You're going from fiber to fiber. It's a Calabi-Yau space. And you approach a singularity of the space because certain spheres are collapsing to points. These become singular in the sense of an ADE classification of ordinary singularity theory. ADE refers to the Dinkin diagrams that determine the classification. And lo and behold, what physics gives you is you actually see the Lie algebras of the ADE sitting there because of the physical Hilbert space. That is leading to some new 4-dimensional quantum field theories, which excites both physicists and will eventually excite mathematicians if we can see them more concretely than one does now. At the moment, it's rather interesting to listen to physicists say, well, this point in the moduli space, this singular point in the moduli space of a Calabi-Yau is going to give a new 4-dimensional field theory that roughly looks like this. That's as far as one goes at the present time. And they'll say this singularity in the moduli space, well, that's a Seiberg-Witten theory. What they mean by that statement and fleshing it out is something that I think is going to take us a long time, and it's that reason that I urge young people particularly to learn both subjects, because as exciting as these developments between math and physics have been in the past, I think they're going to get even more exciting. Okay. So let me begin. Where am I? Right here. Since this is supposed to be a colloquium talk, I will start out very simply and remind you of what the index is. Oh, I was looking for this one. All right. So, Blaine, I'm starting now, okay? So I remind you what the index is. It's the dimension of a kernel minus dimension of cokernel. And I want to emphasize to novices that all this comes from analysis. You would like the dimension of the cokernel to be 0 so that the map T is surjective. That tells you that solutions exist to a partial differential equation. And you would like the dimension of the kernel to be 0. That tells you that the solution, when it exists, is unique. Mathematicians, being very lazy, would like the Fredholm alternative. What they want to say is that uniqueness implies existence and existence implies uniqueness, and that's the case if the index is 0. So it comes as a shock all the time when you don't have index 0. Again, to emphasize analysis, a simple example you should try for index theory is ordinary Fredholm operators on the circle. So take the holomorphic boundary values, Fourier series with non-negative coefficient, and that's your Hilbert space, little L2. Multiply by a function which is invertible on the circle. That'll take you out of holomorphic L2 and project back on to holomorphic L2. And then a nice exercise is to prove that that operator will have an index. That is, that the image is compact and those dimensions are finite. That operator will have an index, and that the index of the operator is minus the winding number. It's the simplest example of an analytic index being a topological index and is an index there. And even that example turns out to be very powerful. It's the basis of Wiener-Hopf theory. But let me go on. I want to get to the heat equation approach to index theory. And a very elementary observation of McCain and myself was that if you had an operator T, then the eigenvalues, the non-zero eigenvalues of T star T is the same as the non-zero eigenvalues of TT star. By going from this equation to this, and you can go backwards when lambda is not equal to 0. So T star T and TT star have the same eigenvalues. And so if f is a continuous function, and you can take functions of these positive operators, then the index of T is just the trace of the first operator minus the trace of the second operator, because the higher eigenvalues cancel, and the 0th eigenvalue contributes 1 to the trace, so you're getting the dimension of the kernel minus the dimension of the cokernel. See, I'm going to have trouble with the incline of this plane. The critical thing is to take the function to be e to the minus tx. So the index t is trace what I've written there. And it's best to think of the whole situation as a Z2 grading with t and t star on an equal footing, if you wish, and the square being the t star t and the TT star, which I'm calling Laplacians because I want to apply the situation where T is the geometric first order operator whose square is Laplacian-like. So I'm assuming the Dirac operator, or D plus its adjoint, on forms decomposed in various ways. We use physics notation and call gamma 5 the projection on the positive on B plus and minus 1 on B minus. Then the index of T is just this expression. The advantage of using e to the minus tx is because we have very good asymptotics for the heat operator. They have asymptotic expansions. And for d even, assuming t is Dirac-like, meaning its square, or tt star is Laplacian operator, then you get out of this expansion that the lower terms have to cancel, and the index of t is simply being the trace. That would mean you would integrate over all x. That's integrating over the manifold. It's just this difference. Just from heat kernel considerations and expansion. On the other hand, those can be expressed in terms of the curvature, because they're all expressible in terms of the metric and its derivatives. The reason for that is pretty standard integral equation for the heat kernel. I'll just put it on the board. The idea here, without my going through the transparency, is you look at a point, freeze the coefficient of the Laplacian, and look at the heat kernel for that constant coefficient operator, and then there's a integral equation for the heat kernel you want locally in terms of the heat kernel of the fixed operator, which I've written down, and from that you can get the asymptotic expansion. And that's what tells you that you're going to get GIJs and all their derivatives appearing. So as a result of this fairly standard analysis, I've lost a page here somewhere. Critical page, actually. As a result of this standard analysis, because the C's involve the curvature and their derivatives, we conclude that the index of T is equal to some integral over m of a polynomial in R, the derivative of R, second derivative of R, etc. And in fact, knowing the scaling in terms of the metric, we can say what the degree of the polynomial is and how many powers of the various things you have to have. McCain and I, when we had got this far, sort of computed special cases and saw that these terms weren't here. And we asked, why not? Why aren't they there? Gilkey answered this question with Gilkey's lemma. And he showed that there is a cancellation that takes place so that the higher derivatives don't appear. And you'll see there's a very nice exposition of the use of Gilkey's lemma and the heat equation methods that McCain and I introduced in Atiyah, Bott, and Patoti. It's a beautiful exposition of this view. Once you have eliminated the covariant derivatives, then you have the statement, really, of the index. theorem. I said that briefly. And so, in fact, we could end there. I've just sketched there are about 4 different proofs of the index theorem by now, and I've just sketched one of them. But I want to make a comment because of the development of Seiberg-Witten. In order, this is a increasing sensitivity session for the next 2 lines, okay? It's very interesting about the heat kernel. If you look at this operator, as t goes to infinity, you kill everything but the 0 eigenvalues. Because the eigenvalues are positive, they're decaying very rapidly, and as t goes to infinity, you're just going to get projection on the 0 eigenspace for t star t. This is the full Laplacian on both, and you're going to get the projection on the kernel of tt star on the other piece. And so, in fact, you could really think of, if you think formally, and you put a gamma 5 in here, which makes minus, you could think of e to the minus t Laplacian with a gamma 5, the limit is t going to infinity, as really the definition of the index. Took traces, it would be. It's the definition of the index as t goes to infinity. Scaling the metric, because that's all it is. You could put the Laplacian scales as 1 over t squared, 1 over whatever the scaling parameter is, and you could bring that t into here and think of it as scaling the metric. On the other hand, if you go the other way, as t goes to 0, then you get an entirely different kettle of fish. You get something local. And what the index theorem tells you is that as t goes to infinity, you're getting the definition of something that's topological, the index. But as t goes to 0, you get something really an entirely different looking object, which is a local formulas for the index. And that's the substance of what I've said so far. Not only that, but notice I never did tell you for any given operator what this polynomial in R was. I just said, just from the information we have, it's a polynomial in R. Rather functorial points of view with characteristic classes, etc., will tell you that if this were the Dirac operator, you're going to put the A-roof genus in here, and you get various combinations of characteristic classes depending what operator you're going to take. Now, what I want to say is the analogy, and it's an analogy which Witten was well aware of when he thought about Donaldson polynomial. That was his way of looking at it from quantum field theory, was to think of the Donaldson-Witten Lagrangian, let's call it, as the analog of this part. That really defines the theory for you. In no way does it compute the invariance, but it defines the invariance from the point of view of quantum field theory. You take this field theory and then you scale a metric. That's what this does. This scaling is making the manifold very large, so locally it looks flat. You scale the metric, and without much, you have some general form of what the answer has to be. Most of us, certainly most of the topologists, want to know the details of how you go from Donaldson-Witten to Seiberg-Witten to see how you're going to get that Lagrangian and those equations of motion. That's not what physicists do. Just like it would be pretty killing to take an 8-dimensional manifold and directly try and compute the coefficients that are going to occur in the heat kernel to see what particular polynomial you're going to get. You just have an entirely different machine of characteristic classes to tell you what it is you should do once you know the general framework. And that's what happens in the Donaldson-Witten theory. You conclude from what the renormalization group, that scaling, is supposed to do for you, you conclude that it's got to be a field theory which has certain properties, and that field theory is supposed to be unique, and so it's going to have to look like that. And in fact, if you read Witten's early papers, he was looking for the right framework or the right restriction of the possibilities when he was studying the case where the manifold was Kähler manifold, was Kähler, in order to see what that field theory looked like. It was only when Seiberg had introduced the right holomorphicity that he saw what the answer should look like, and that's what led to Seiberg-Witten. It wasn't a kind of brute force computation. Okay. Now, I've given you an exposition of where we were with the heat kernel method. I myself, Gilkey, in fact, was a grad student at Courant, and he showed me his cancellation lemma for the Euler index, d plus del. Patodi had actually done it by brute force, and Gilkey had understood that he could do it more abstractly, and I said, my God, it's what you've shown me is probably easier for the signature operator, and once you know it for the signature operator, you're in, because of k-theoretic considerations that all operators are generated by the signature operator tensored with vector bundles. And Gilkey, in fact, the next day, I think, or next week, showed me, in fact, that worked. And so one had a proof of the index theorem by heat equation methods. Nevertheless, I was very unhappy with Gilkey's lemma in the sense that it didn't teach me anything. You know, okay, here's a lemma that explains the cancellation. I was happy to see the theorem proved this way, but I didn't learn anything, and I thought there was some deeper reason for the cancellation, and I sort of idly, not seriously, looked for it, and I didn't find it. Well, the deeper reason is supersymmetry. And so now what I want to do is, having described this heat equation proof, I want to do it from an entirely different point of view, and I would like to introduce these two new categories that I talked about, supersymmetry and string theory, and let's see what it gives you. So I'm going to talk about first the category of supersymmetry, but in quantum mechanics, because I don't want to get to string theory yet. So we're going to talk about supersymmetric quantum mechanics. And first what we have to do is talk about path integrals. And I remind you of the mathematical aspects of that. We have Wiener, who expressed the heat kernel for a Laplacian in terms of a path integral. I'm writing the physics expression for paths for Wiener measure. And it extends a la Feynman-Katz for a Schrödinger operator where you have a Laplacian plus potential function. Here is again, there is in fact a well-defined measure so that this is integrable, and will give you the heat kernel for the Schrödinger operator. For a vector bundle, you have to do something a little more complicated. So suppose that we have a vector bundle with the covariant differential, that is a connection. Then how do we get the path integral for the kernel of e to the minus t d star d? This development is due to Ito, Malyavin, and Struck. And what you do is put in parallel transport along gamma. So remember what you've got. You're talking about an operator which is a Laplacian, but it's a Laplacian on sections of the vector bundle. So you got to have something which will go from the fiber at y, or vector at y, to a fiber at x, And that's just what this does. It maps, parallel transport maps, if you have a curve gamma, will map you from the fiber at y to the fiber at x. And that's the formula for the heat kernel for that operator dd star. If you have the spin vector bundles, assuming you have a spin manifold, then you could talk about the connection restricted to positive spinners versus that I'm on an even dimensional manifold versus negative spinners, and you would get this formula for the difference of the two traces. A la, and by the way, I emphasize all this is well defined. These integrals exist. You're only talking about paths, not about maps of higher dimensions in the space. On the other hand, the Dirac operator is not covariant differential times its adjoint. It differs from it by the scalar curvature, and so you have a sort of potential function given by the scalar curvature. So you have to make that modification in the formula. And so you get this formula for the index of the Dirac operator, or again, for any operator of Dirac type. Geometric, elliptic, first-order operator whose square is a Laplacian-like. The index is equal to this. Here is Feynman-Katz. Here's the extension a la Ito, Mayovan-Struck. And now I only want to make one further comment in order to get to supersymmetric quantum mechanics. And that is that for a spin manifold, that if you took trace of parallel transport around a curve on spinners, minus for positive, minus negative spinners, then this is the square root of determinant 1 minus parallel transport for vectors. This is a purely group theoretic statement. Let me emphasize that. It says that you have the orthogonal group, you have the spin group, that if you look at the representation of the spin on plus spinners, take its character, subtract off the representation on minus spinners, take its character, then what you'll get is the square root of the determinant of 1 minus the ordinary. The projection on the orthogonal group is what this says. Now we want to do this for all paths, and so the question is which square root, etc. And in fact, if you're just looking at a Ramondian manifold and try and take the square root consistently, you'll find the condition that you can do this consistently is that the Ramondian manifold be a spin manifold. That's just what that question of the sign of the square root really does for you. So finally, we end up with this formula for the index of the Dirac, looking at the heat equation from the point of view of a path integral. This is a correct, meaningful formula in stochastic integrals, but it's not easy to compute with. There it is. Okay, it's a formula for the index. It's very hard to compute with. Now we can talk about quantum mechanics, about supersymmetry. Physics tells us that if we want to compute trace e to the minus t Laplacian gamma 5, which I had defined, that one should integrate in a new category. We could integrate supercurves with appropriate superaction and supermeasure, and the index will turn out to be this integral, which I haven't defined, where the new action is a superfunction rather than an ordinary function. Here, this means the length squared of the curve. That's the ordinary action, kinetic action. But here is something brand new for most mathematicians. This is not a function at all. What this is in the super category, it's really a supersymmetric function of the size. So let me explain mathematically part of what's going on here, and then I'll say a few more things in the next transparency. So what we have is curves, but we've added to curves something else. Psi is a vector field along the curve. I remind you at the beginning I said that's a tangent vector to loop space. So we're now talking about a vector field along the curve. If we have the vector field along the curve, it comes with its connection. So if I say all this mathematically, gamma is a curve from S1 into the manifold M. We can pull the tangent space back to S1. Psi is a section of this. That's a fancy way of simply saying that I have a vector field along the curve. The reason I'm saying it this way is T of M has a connection on it, the Ramondian connection. So when I pull it back, I've got vector fields along S1 with a connection, and so I can take its covariant derivative along the curve. That's what this symbol means. Gamma, little gamma dot, means that index is along the tangent vector to the curve. So, a supercurve is just a vector field along the curve gamma. That is a tangent vector in loop space at gamma, a tangent vector in loop space to the curve gamma. This expression I wrote down means the 2 form on this tangent space, which sends a pair of vectors into this, the inner product being the usual thing along the curve, integrated over the curve. And you think of that not as a function, but really as a skew-symmetric object that is a 2 form. And the reason you want to think of it that way is that you want to interpret what this expression means, integral over these vector fields along the curve. And what you do is take your Q from finite dimensions, that if you have a skew-symmetric matrix, what you mean by this integral, called a Berzin integral, is you want to think of this as a 2 form, the exponential of a 2 form in the Grossman algebra, and then you take the top part of it in the Grossman algebra when you expand the exponential as a power series. But power series now means as a 2 form, so it's 1 plus a 2 form plus the square of the 2 form over 2, etc., to the top. And you'll find when you do that, that this is just a neat expression for the Pfaffian of Aij of the skew-symmetric matrix. And so, by analogy, what this expression means is the Pfaffian of this operator. Lemma. The Pfaffian of that operator is equal to the square root, the expression we've seen before. The square root of the determinant of 1 minus parallel transport around the closed curve. Now again, that's a nice exercise for you. Complicated operator, dd theta. You surely don't want to try and compute its eigenvalues directly and see what the square root of the determinant is. What you do is this. Think about connections along a curve. You have some freedom of gauge transformations along the curve. Turns out that the only thing that determines the connection up to gauge transformations is just parallel transport around the entire curve. Because if two connections had the same parallel transport around the curve, then if you looked at one times the inverse of the other, that'll give you, along the curve, that'll give you a gauge transformation. So the only thing that determines the connection up to gauge transformations, and therefore this operator up to similarity, and therefore the Pfaffian, is just parallel transport, or total parallel transport around the curve. Well, in that case, if you have parallel transport around the curve, some rotation, the best thing to take for the connection is the one which is constant. Just think of the curve, think of this curvature, this R, this orthogonal transformation, this rotation, as the exponential times some skew matrix, and take e to the t of that skew matrix as you move along the curve. That essentially reduces the connection to constant coefficients, and you diagonalize and you reduce to the 2 by 2 matrix case with a constant coefficient. So you're not talking about anything more than d dt plus some constant. That's the operator you're looking for. And there you can immediately write down what its eigenvalues are, compute the Pfaffian, and see that the theorem is right for that operator, and therefore for products of such operators, and therefore the lemma is proved. So we conclude that the physics path integral and the math path integral are the same, except for this scalar curvature part, which is harmless as you let t go to 0, which is what we're going to do. So why look at it from this physics point of view? Well, there are 2 points I want to make, even though I don't have the language or the insight I can provide you from physics. Physics tells you automatically that that integral, that supersymmetric, that superpath integral I wrote down, has to give you the index of Dirac. The idea is that there is a supersymmetry of this Lagrangian. Physicists write this supersymmetry in infinitesimal form like this. Tells you what the variation of the curve should look like. This one you would expect. It says if you move the curve, you're going to move it along some tangent direction along the curve. This one is a little more complicated. This is a variation of the odd elements. Mathematically, it actually turns out that this supersymmetry is a very nice operator that we've seen before. You're looking at the tangent bundle, which is the same as the cotangent bundle because of the metric. And then we have a time-honored, we're looking at sections of it, so we're looking at forms on loops of a manifold, and then Q turns out to be D plus interior product of the vector field that you have on loops of a manifold, namely the tangent vector to the curve. And in particular then, that Q squared is the Lie derivative of that vector field, which is just dd theta along the curve, and so Q squared will be the Hamiltonian for this system. And what physics says, and I urge mathematicians to really perhaps begin their study by doing classical and quantum mechanics in this new category. What physics says is, just like you have Noether theorem that gives you a current and a charge, you've got super Noether, which gives you a supercurrent and supercharge, and the quantization will automatically send Q into the Dirac operator, and the superpath integral gives the index of Dirac. So once you think about superquantum mechanics, one would immediately write that path integral down. I think I have a minute to tell you that the idea, as far as I can tell, goes back to Witten. In fact, in a Solvay conference in Austin, Texas in '83, Witten explained these ideas to Atiyah and I in rather strange circumstances. There was a barbecue and a rock band where we were eating, and Witten was shouting to Michael and I, trying to explain this in this din of a rock band. And what he was saying was so remarkable that, of course, we were quite excited by what he said. Atiyah interpreted Witten's remarks at the time in a very beautiful paper, which I can summarize as saying, if the Doister-Mott-Heckman localization theorem holds for loops on a manifold, the index theorem follows. No one has proved that that holds, so that's just an insight or way of looking at what I've just said to you. I, on my way home from Texas, stopped in Chicago and met Dan Friedan and Paul Windy, and I explained Witten's ideas to them, and they wrote a very nice paper exposing the entire subject. Alvarez Gomez, I don't know whether he independently arrived at this set of ideas or whether he was also influenced by Witten. But what I want to emphasize, and I can only say it a couple times because we don't have the background to explain the details, that it's automatic, that this superpath integral has to be the integral that will give you the index of the Dirac operator. And I've shown you, I hope, why when you interpret it right, you will in fact get the formula I wrote down before. Now the punchline. Why do it? We still haven't got the formula this way. The punchline is that since it's topological and since this formula is independent of t, then let's see what happens when we let t go to 0. The whole point of loops is you want to see what happens when they get small. They collapse to a point. So physicists feel, since this thing is independent of t, let's take t going to 0 and see what happens. So the expectation is that the semi-classical approximation, what you will get as t goes to 0, should be exact. Now, the semi-classical approximation, mathematicians really understand in their own language. What you do is look at the critical points of this action, in this case, where it's 0. What will that be? That will be where the loops become points. That's a manifold, but we have this extra condition of vector fields along loops, so we would have a vector field depending on time at the point 0, but we'd want it to be constant. Then the derivative would be 0, because there's no connection part. We'd just be taking ordinary d dt. So where that action collapses to 0 is simply the tangent bundle to the manifold. Then we have its normal bundle at the point, which is easily described. It's simply sort of functions of the circle into the tangent bundle, let's say at this point, but which is orthogonal to the constant ones. So those are the ones whose integral will be 0. And then what you do is you replace, here the action is 0, you replace the action in the normal bundle by the Hessian, so it's quadratic. So what happens in the semi-classical approximation, which is the one case you can compute in quantum field theory, is you have the classical stuff here. Here you have something which is quadratic, which you can integrate out, and then you'll get some determinants, and as a result, when you integrate over this space, you'll end up with a formula in the semi-classical, which you can evaluate in the semi-classical case. What that looks like is this. I've spelled out here what I've just said. I don't think I'll tax you with going through the details, but because you end up with the quadratic stuff, you end up with determinants, and when you compute this determinant, you end up with this expression, which is in fact the A-roof genus. You want to think of the curvature, a matrix of two forms, and this expression is in fact the A-roof genus. You integrate over the manifold, and so the semi-classical approximation here indeed gives you the formula for the Dirac operator. So let's review what so far supersymmetric quantum mechanics does for you. One, if you know what it is, you're kind of automatically led to the path integral formula, supersymmetric path integral formula for the Dirac operator. Two, you expect, because the index is topological, that the semi-classical approximation should give you the right answer. It does give you the right answer. The only thing that's left is, why is the semi-classical approximation exact from a mathematical point of view? That, in fact, turns out to be the case. And it was, from the point of view of path integrals, a theorem in stochastic integrals due to Stroop. The other approach that one learns here is, rather than the Levy method of iteration that I described in a transparency, where you freeze the coefficients at a point, look at the Laplacian on the tangent space, it's better, and this is the insight of Getzler, to use the Laplacian with frozen coefficients, but I should have had a UK, a quadratic term, should be something quadratic here, UK wedge UL. This means Clifford multiplication on spinors. And that if you use this operator, this Schrödinger operator, rather than just fixing the Laplacian, then you get a much better approximation to the heat kernel, and you hit the curvature terms without covariant derivatives. That's really what the Getzler point of view gives. Peter van Nieuwenhuis just gave me an 80-page paper on quantum mechanics, path integrals, and making them rigorous from a physical point of view. And I have to say that in 24 hours I haven't absorbed that yet. I should say, and I meant to say at the beginning of this talk, the low energy, I've talked in this case about what happens in the semi-classical approximation, or as you'll see in a minute, when you bring loops down to a point. The low energy limits of a couple of these string theories are what are called supergravity theories, and it's Peter and Dan Friedman here about 20 years ago who first discovered supergravity in 4 dimensions and developed that theory. And now in 10 and 11 dimensions, these have exciting connections with string theory. All right. I am going to take a few more minutes. Since from my point of view, I started late. Let me tax you a little bit more. I've just explained to you how adding the category of supersymmetry really illuminates the index theorem. It certainly answers my question of what Gilkey's lemma was all about. It just avoids all that completely. It just gives you the answer right on the nose. Now let's put in the other category, right? So now let's put string theory in. Remember what string theory is supposed to do. I'm going to put it on transparency, but let's just say it. I start with a manifold. I talked about Dirac on the manifold, and I talked about the path integral formula for the index of Dirac. I want to replace the manifold by loops on a manifold. I want to replace Dirac by the corresponding Dirac on loops on a manifold. That's called Dirac-Ramoned. I want to compute its index. I want to get the path integral formula for that operator. And path integral means I want to talk about loops on loops of a manifold. In other words, I need to talk about maps of a torus into the manifold and corresponding path integral. Well, I don't know whether you guys are fading, but my transparencies are. So, I'm going to add the new category. I'm going from the manifold to loops on a manifold. And I end up with maps of a torus into the manifold. I want to talk about the analog of the Dirac operator, the Dirac-Ramoned operator. I won't even try and define it because its existence for an arbitrary manifold, even a spin manifold, is problematical. Nevertheless, I want to talk about an analog of an action, and I want to talk about the analog of the supersymmetric quantum mechanics action. Well, the action's very pretty. I'm going to have to integrate over a torus. There'll be a kinetic term. This is what's going to occur. The kinetic term, this is really the differential of x norm squared, but written in complex way, because I want to emphasize the complex structure of the torus, not the metric on the torus. Then I want that term that's going to be skew symmetric. These will be, for starters, this will be vector fields along the torus, along x, the torus, but it isn't in the right space. What I need to do is tensor it with a spinner, lambda 1/2 0, that is the square root of the canonical bundle. So I have to pick a spin structure. And what I really want is a half form that is a spinner tensored with a section that is a vector field along the torus. And the reason is I want something that's skew symmetric. If I take d bar, and what do I mean by d bar? I meant, well, d bar on this part and on this space has a connection, so it's coupled to fields along the torus. And as a map, what will d bar do? It increases this by 1. So I'll get something in 1/2 comma 1. But in fact, that's the dual space to this object, because if I had something of 1/2 0, if I multiply with this, I'll get something of type 1 1. That's the volume element on the torus I can integrate. I integrate and, of course, contract the tangent images. And it turns out that this operator is skew adjoint, so we have the analogy of what we had in the supersymmetric quantum mechanics case of a kinetic term plus a super partner, so to speak, something which is a two-form on the appropriate space. This was carried out in a lovely paper by Alvarez, Killingback, Mondano, and Windy. And what happens is this. Now, in this case, because we're dealing with maps of a two-dimensional object in, two things don't exist. And you'd think if we were mathematicians, we'd give up. One thing that doesn't exist is the Dirac-Ramonde operator on loops on the manifold. The other thing that doesn't exist, for mathematicians anyway, is integration over maps of a two-dimensional object into the manifold. Neither exists, but the semi-classical approximations of both exist. The semi-classical approximation of the Dirac-Ramonde operator is this one. What you do is replace loops on a manifold, as you'd expect, by constant loops, that's the manifold, plus the normal bundle. Again, the normal bundle will simply be a vector space at a point which are functions of a circle into tangent vectors whose tangent vectors at the point whose integral is 0. That's what the orthogonal complement to the manifold is. And then what you do is replace the original operator by the Dirac operator along here, and the corresponding Dirac operator along here, which you can write conveniently as d bar plus wedging by dz bar plus its adjoint. So you really have an operator on this space that's well defined, Dirac on the base, and a family, a field of elliptic operators along these fibers. Moreover, you have a circle action, because circles act on loops, and you trace by rotating the loop. If you trace that, what will happen is that, of course, on a constant, it's constant, but there's a rotation in here. And so you can ask for the index of this family of operators. It's well defined. But now you need the G-invariant index, that is the S1 index. You want to know the index of the operator on each representation of the circle. So this will be a power series with AN being the index of the operator in that representation. And now what these four people did was compute the semi-classical approximation, and what they found was the elliptic genus formula for the S1 index of this operator. Moreover, they found that that operator, that formula, as a function of S1, of characters, was modular, and it comes out automatically because the only thing you used about the torus was its complex structure. So modular, so it's modular, and SL2Z operation will have no effect. That is, here's what they did. They took the semi-classical approximation for the action I described before. They found, just like we did earlier, that you end up with the Pfaffian of this operator. You can actually compute what that Pfaffian is when P1 is a manifold of 0, and you get this series with Eisenstein, with GK being the Eisenstein series, and that is in fact the elliptic genus. And as I emphasize, the entire expression from physics only depends on the complex structure of the torus, so you get modularity free of charge. It's interesting that this paper, these results were known. They talked about them, although they didn't write up the paper. Before Witten's interpretation of the elliptic genus as the S1 index of an operator, they just had this formula directly from the extension of supersymmetric quantum mechanics to string theory. So I think I've illustrated my point about the power of these two new categories in mathematics. I have one more transparency I want to show you, and that is, so that we get into string theory, we had an action that was just the first two terms in that expression, but we don't really want to side with lambda 1/2 zero spinors. We should take its conjugate and so have this term as well, where these lie in the other conjugate of the other square root. Here you would have two symmetries. One is called of type 1, 0, the supersymmetry I didn't write down for this theory, this part. Another of type 0, 1. But the general principles from physics tell us that these two things should anti-commute. If you really want that to happen, you've got to add another term. R is skew in Ij and KL. Here's skew in Ij, skew in KL. But when you replace Ij with KL, this pair commutes with this pair. Just the right kind of symmetry properties to add that term. And now we have defined for you the type 2 superstring, and in a way I've indicated it has two supersymmetries, just from the point of view motivated by index theory. Thank you for your patience.
Just say a little bit about the Dirac-Ramoned operator, when it's supposed to exist. I mean, what is the conjectural
I don't think anybody knows anything about it. Remember, the one I didn't have time to say is that it's not just what you would think of Dirac being, but you would add to it a potential term because you've got a vector field, natural vector field. You would add Clifford multiplication by gamma dot. And formally, I mean, you would write this, if you had a Hilbert space, you'd write this. Remember, you write usual Dirac, you write is a summation of Clifford multiplication by Ej partial with respect to Xj. So here you would write sum of, if you had spinor fields in an orthonormal base, you'd write summation of Cj, and then you'd need the analog of partial with respect to Xj, however you want to write that. Formally would be the operator plus this term. Well, in a free theory, I mean, if the target is Euclidean space, remember I was emphasizing where the target is a curved Riemannian manifold. If the target is Euclidean space or Minkowski space, then there are no problems of writing these things down formally, because you have a Hilbert space, you have the oscillators, you have the whole formalism of dealing with the correct ordering with the operators, etc. So you can write it down when the target is flat. But I was saying it didn't exist when it was Riemannian, as far as I know.
So what is the first Pontryagin number of the manifolds play a key role?
Yes, it does. Let's see, where does it occur? There's an infinity in the definition, an honest infinity when you try and compute determinants, and the only way you can eliminate it is when P1 is 0.